Welcome to Industrial Networking Basics, a series of progressive network design considerations. This series covers networking basics, not so basics, best practices, useful industry networking trends and technologies that every automation professional should be aware of. Welcome to the third presentation in the Progressive Network Design Consideration series. In today's presentation, we'll be talking about topologies and media redundancy. But first, a recap of where we left off. Networking a handful of devices into a single standalone machine is a snap. The same applies when networked into a production cell. Getting this then tied into the rest of a production line can be a little bit more of a challenge, but still very feasible. And when asked to network this and all of the other production lines devices into the rest of the plant, ideally so that all are accessible via a plant backbone network, this is definitely a little bit more of a challenge, and yes, it obviously needs additional education. And this is why we're here to look at different topologies available to us. There are four fundamental topology designs: the linear topology, which is effectively a daisy chain, and the star, also known as a hub and spoke or tree topology, are probably the most common. This is due to the fact that they are supported by all Ethernet networking hardware. A ring and a mesh, on the other hand, are a little bit more recent and require a more intelligent networking device to prevent loops, such as a managed switch. But more on that in a few slides. So let's talk about the benefits of each. The linear topology is simple in all definitions of the word. It is simple to design and simple to troubleshoot when something goes wrong. The downside is rather obvious. An outage of a switch due to a simple power failure or a switch failure, or someone unplugging or severing the network cable, or a combination of these, will result in the up and downstream devices unable to talk. The star or hub and spoke topology is something that we see in many plants that have existing networks dating back to the 80s and early 90s. This is largely due to this having been the de facto topology standard for office networks. And as you can tell, this has one glaring vulnerable point of failure, that being the core switch. Other downsides of this topology design is that the amount of cabling that is utilized and the associated cost of having to pull additional segments for new networking devices. Meshes. This is something that we see as the unfortunate consequence to unplanned loops due to poor network drawing documentation. Thankfully, RSTP, or Rapid Spanning Tree Protocol, detects these loops and through an algorithm calculates an active network path between devices while putting all other loop network connections into a blocked or a discarding state. While beneficial, Spanning Tree really has no business on an automation network for two primary reasons. It is often too slow to recover for most applications, and depending on the network size, it can take anywhere from half a second to several seconds to recover. Additionally, because Spanning Tree elects a switch as the root bridge which governs the Spanning Tree algorithm, a network can oscillate if there are more than 20 hops or switches from the root switch to the network edge, or if the root bridge switch is removed, or if one with a lower priority is added to the network, making it the root bridge and forcing the algorithm to reassess the links, causing a brief outage through this entire oscillation. These oscillations are commonly seen in improperly configured networks or ones that do not have proper plant office network convergences. And this brings us to rings. Rings are a very simple yet effective topology design that is inherently redundant, with one segment having a standby link and thus averting a loop. There are several dozen proprietary redundancy protocols out there that support the ring topology, with only a very limited number that are a true industry standard. So word to the wise, pick your redundancy technology carefully. So why have rings become so well adopted in industrial applications? Well, for starters, they negate issues due to media failure, such as accidentally unplugging the wrong link or severing a cable, having a switch fail, or having a power outage. And such network outages have far greater consequences in an industrial environment than in an office environment. So what is needed is a redundancy protocol that is fast, predictable, as well as repeatable. But what happens if we don't have a redundancy protocol managing our network? Let's take a look at a quick demo. So this demo that I pre-recorded shows a PC pinging a PLC, and these are connected via a series of managed switches in a linear topology. And hanging off of this linear topology, I have an unmanaged switch, which is hanging off of one of these managed switches, and I'm going to create a loop on that unmanaged switch via a simple patch cable. This is something that happens to so many customers so often, and I'm just going to visualize for you what actually takes place on the network, showing Wireshark, which is the chart that you see here, and we'll take a look as to what actually transpires on the network. So what you're seeing on the left is the ping. You're seeing the graph here. This is just the overall throughput of Wireshark. There we have a loop, and it took the traffic from about 12-ish packets per second to over 100,000 packets per second. And this is simply by creating a loop with a patch cable in the unmanaged switch. This will guarantee that all traffic on the network will cease. This is more than most automation devices, at least all the ones that I'm aware of, can possibly handle. So disconnecting the loop or breaking the loop and then fast forwarding the video sequence, we then see the devices recover and the traffic resumes back to about 12 packets per second. So, knowing that a loop in your network is bad and the resulting broadcast storm is a really bad thing to happen to your network, you clearly need to have a redundancy protocol. But which is best? Let's look at your options. First off, we have all of the proprietary ones, of which there are many. And most all are ring-based, with each one being unique to their own specific vendor, and most with claimed recovery times that can only be replicated in a controlled lab environment, typically never in a real-world deployment. What all have in common is that they all require all of the switches to be managed, and that they all need to support that given vendor's redundancy protocol. Also, one switch is designated as the manager of the ring, holding a ring segment open, waiting for a segment to fail. Once this happens, a command is issued to all of the switches to dump their MAC address tables and relearn what MAC addresses are associated with each of the switch's ports. With networks having hundreds, thousands, or even tens of thousands of devices, there's obviously a lot going on in the background when this happens. So, what proprietary protocols are out there? Well, it all started in the late 90s when Hirschman developed the world's first redundant hub-based ring. And it needs to be noted that switches did not exist back then. The protocol was called hyperring, and there were no standards fast enough, hence this proprietary redundancy protocol. And fortunately and unfortunately, due to the proliferation of Ethernet in the industrial spaces, other vendors emerged, each developing and promoting their own flavor of hyperring. And as with most things that are proprietary, there are certain consequences. So the short answer to proprietary redundancy protocols is to avoid them as best as possible, because you will be tying yourself and committing yourself to that one vendor. Next, we have MRP, or Media Redundancy Protocol. This is an IEC 62439 spec that provides data recovery in as little as 10 milliseconds for smaller deployments, but a maximum of 200 milliseconds for larger deployments in networks of 50 ring switches. This obviously does not include additional switches that are then hanging off of the ring, so we're talking about some very sizable networks. Aside from it being an open standard and supported by multiple industrial vendors, MRP is ideal for many other reasons. It is easy to configure, the recovery is predictable, it can be converged with other redundancy protocols, it is easy to troubleshoot, and can also be integrated into additional MRP rings for a larger multi-ring topology, but more on that later. And then there's spanning tree. So RSTP, or Rapid Spanning Tree Protocol, is something that we've discussed previously. It has its benefits, but really has no purpose or benefit on an automation plant backbone. Next is DLR, or Device Level Ring. This is a vendor standard developed by Rockwell and promoted by the ODVA. DLR allows supported devices that have an integrated 2 or more port switch to create a fault-tolerant ring with very fast recovery. As it is optimized for a very finite number of automation devices, it is rather vendor biased and requires the use of a switch with DLR support to integrate non-DLR devices into the ring. Then we have HSR, which is very much like all of the other redundancy protocols, but only in the fact that it is a ring. And unlike the other redundancy protocols that transmit in one direction of the ring, HSR is able to send an Ethernet packet into both directions of the ring, with the receiving device only accepting the first received packet and discarding the second. HSR, like MRP, is part of the IEC 62439 standardization and is an optimal protocol for use in applications that are absolutely mission critical and subject to faults if a single packet is missed. And lastly, we have PRP. PRP, like HSR, sends out duplicate packets, but instead of sending these out into a ring, PRP sends these packets out into two distinct networks. One could be the plant network, the other being possibly the office network. And like HSR, PRP will only accept the first received packet, discarding the second packet. Due to the reliability that PRP and HSR provide, we're seeing several automation vendors adopting these protocols for the deployment in their devices in mission-critical applications. This is most notably seen in the power automation and power utility industry. So, which is best? Best is obviously one that is not proprietary, and best for approximately 90 to 95% of the applications that we see, and this is MRP. It is best due to the simplicity, the speed, predictability of the recovery, ease of troubleshooting, and the fact that it is supported by several vendors, including Cisco. It can even operate in a mix of copper and or fiber media, and a variety of mixed speeds, all the way up to 10 gigabit. The configuration is also extremely simple. With the ring open, you enable the redundancy protocol on all of the switches. Select one of the switches to be the ring manager. Select the ring ports on all of these switches, any speed, fiber or copper. Disable spanning tree on the ring ports and only on the ring ports, keeping spanning tree active for the local ports, preventing loops happening on the switch. Close the ring, confirm the redundancy, and then save the configuration to all the switches. One can easily configure MRP on a switch in as little as 30 to 45 seconds. So taking what we have learned, we can apply MRP to our production line, creating a ring and making note of twisted pairs maximum 100 meters. If we go beyond that, or even if we're close and there's electrical noise, it might be best to have that long segment be fiber. Or you can get rather creative with the links and the way that you build your ring. Next, let's apply the same to the other production and process applications, keeping in mind that we'll also want to segment these when we learn about VLANs in an upcoming presentation. Like the various rings, plan the plant's core backbone to touch as many of the individual rings as possible, and in as many areas of those rings as possible, because we're going to look to redundantly link those rings to the plant's ring next. Given this, a theoretical plant backbone would look something like this. Assuming that the maximum fiber segment is well under 500 meters, We would use either OM2 or OM3 multimode fiber, and we could then use gigabit. And these are topics from a previous presentation. By connecting the segmented networks onto the backbone ring via two connections creates multiple levels of fault tolerance. So let's look at the options available to us for redundantly connecting these rings. Of the available means, one is redundant ring coupling, which allows two MRP rings to be redundantly connected via two paths, whereas subrings allow multiple MRP rings to share one or more common links. As shown here, you can connect one or more subrings to the main ring. And then we have Ring Coupling Protocol, or RCP, which allows two rings of any standardized protocol or protocols to be redundantly coupled, meaning that one ring can be DLR, the other ring can be MRP, the other can be RSTP, the other can be HSR, and so on and so forth. And it goes without saying, any of these network segments can be any mix of copper and or fiber and speed. So it gives you a ton of flexibility in designing your networks. So, because we do not necessarily want to have a shared network segment, as you would have with a subring, in this instance we would prefer to use redundant ring coupling. This way we would only have the reporting data come into the plant backbone, keeping all of the PLC to drive communication on a production line to its own network. And, just for good measure, let's also make sure that we have sufficient wireless coverage in the warehouse space for their barcode readers, tablets, and any potential AGVs that they may have. And this is what the individual networks would look like. This really was not too difficult, was it? Admittedly, there is quite a bit more to networking, but the core concepts are what we just did. And yes, in many instances, the first steps of mapping out a network is done with a top-down view of a plant network. Oh, but wait, that's right, we have yet to talk about segmenting. And come to think of it, we also have a lot of other topics that we need to look at, such as NATing and so on. And we need to secure the network. And there is a whole lot of other needs, such as convergence into the network office space, and the engineering network, and who's going to monitor and manage all of this. Yes, there still is a lot more to cover, and for this, join us in the next video of the Progressive Network Design Consideration Series to learn more. Thanks for watching.